So the core things to know for chapter 21 is really about resistors and this guy named Kirchhoff. We want to know how to add resistors if we just have resistors inside of a circuit, similar to how we did capacitors. If I add up resistors in series, add up normally. So if I have 3 resistors, I just straight up add them together in series. This is different than capacitors. Remember, capacitors added kind of weird. And then if I want to add resistors in parallel, 1 divided by R parallel is equal to 1 over R1 plus 1 over R2 plus however many resistors you have. So when you're adding resistors in parallel, you have to add up the reciprocal and then take the reciprocal of that to get the actual parallel resistance. And then other things to keep in mind, V in parallel is constant, same as capacitors. It's the same voltage through parallel parts of the circuit. And then current that you got. What's a good letter for current? I. I is current. Drive an English major crazy. Current in parallel splits. And this is happening actually inside of the human body all the time. The human body you can treat like a bunch of resistors, capacitors, all sorts of circuit elements. So you could do biomechanics with this kind of stuff, bioelectronics. Let's see, other things, other big concepts from this chapter. We want to keep in mind the concept of something called EMF, or electromotive force. That's how much kind of voltage you have inside of a circuit. And the voltage you actually get out of a circuit is equal to the EMF inside of a circuit minus I times little r, where little r is some internal resistance of whatever kind of object you have. So EMF. EMF is kind of how much of a rating you have for how much voltage you can get out of something. So on a battery, it gives you a voltage value. The voltage value it gives you is 1.5 on this battery. That would be its EMF. But then if I measure the voltage that I'm actually getting across this, that's going to be what V actually is. And the EMF that you actually get out is decreased just a little bit by the current and the internal resistance of this battery. This battery resists charges flowing through it a little bit, so you get a little bit less voltage than the maximum that it's rated for. Okay. So you can think of V is the actual value, whereas EMF is the ideal value if everything were perfect. We can get objects that have this perfect EMF if we make them really, really cold. They're called superconductors. We'll talk about those maybe a little bit later. So these are big concepts. And then the other addition that we want to be aware of, we want to remember there's a law about electrical circuits called Ohm's law, V equals I times R, current times resistance. And we use this Ohm's law constant in something called Kirchhoff's laws. Kirchhoff's laws are how we add up voltage inside of a circuit. And there are 2 of them. Your book, I think, calls them Kirchhoff's rules. Rules and laws, same difference. So Kirchhoff's laws / rules, we've got the junction rule, which tells us current into a junction is equal to current out. And then we also have the loop rule. Which says voltage in a loop is equal to 0. And we can use these laws to map out what's happening inside of any circuit and figure out everything that's going on inside of it. Practically, we use something called voltmeters to measure voltage. Across the circuit. And we use something called an ammeter to measure current in a circuit. So these are important distinctions, across versus in. And let me show you what that means. So finish writing that down, and then you probably all have to get up and come up closer so you can see the little circuit that we have. So Kirchhoff's laws, or rules. First law rule, current into a junction equals current out. And the loop rule, voltage inside of a loop is equal to 0. And we're going to see an example of this. And we're going to use voltmeters to measure voltage across a circuit, and then ammeters to measure current inside of a circuit. So what that means really is these ammeters, they have to actually be inside of your circuit. You put them in between wires. You actually put them inside of your circuit. Whereas a voltmeter, I can hook up an entire circuit, and then I can come along with a voltmeter, and I can measure the voltage across different parts of the circuit. I don't have to include the voltmeter in the circuit. I do have to include the ammeter. This is going to be relevant for your lab next week. Great. Any questions on any of this? All right, how many of you have seen one of these? Do you know what this is called? Just seen it. You haven't anybody seen it before? You've seen it. Do you know what it is? What it's called?
I'm guessing it detects how much.
So this is called a multimeter. It's kind of neat. It measures voltage. It's the V. Voltage over here. It'll measure current. So there's a little A for amps on this part of the little dial. And then it measures this little thing. What's that letter? What does that represent? Anybody know what unit that is? It looks like this. Omega, which is ohms. And what do ohms measure? Resistance. So this little tool, it can measure V, it can measure I, and it can measure R. Whose law is this? V equals IR? That's Ohm's law. So you can use this to do everything you want to do involving Ohm's law. What you can do is you can hook up a circuit. So that's what I've done here. I've got a circuit. I've got here this little thing right here. And you can get closer if you want to. It's up to you. This little thing has a little MA on it. What does A stand for? Amps. And what is the M? Milli. 10 to the minus 3. So this measures milliamps. So what physical thing is this measuring? Is it V, I, or R? I. This is going to measure the current. And what I've done is I've got the wires going through this. This is inside of my circuit. It's a part of it. I've got a little light bulb. What are these? Batteries. Each one of them is 1.5 volts. How many volts are inside of this? In a perfect world. 3 volts. How'd you get that? Add the 2 batteries together to give me the total voltage that I ideally am getting out of this. And then I have another wire that comes to here. What's this? What does this look like? Looks like a little switch. So right now the light bulb isn't on. There's nothing being measured on this little ammeter because of this little switch. So I have this battery hooked up, but I need charges to actually flow. I need charges to flow through the battery, through this wire, and then they reach this point. What happens when they reach this point? Can they go anywhere? No. So the circuit isn't complete. How do I complete the circuit so that the electrons keep going through the wire, go through the ammeter, through this, through the light bulb, light it up, so that we can get lit and then go back to the battery, complete my circuit. I need to connect everything so everything conducts. Metal is a conductor, so if I move this switch down, what should happen as soon as the metal touches metal? Light bulb should light up. Yay. Not as exciting as the lightning demo. What happened to the little meter? Let me turn off the current, turn off the light bulb, see the little dial, and then I connect the circuit. What happens to the dial?
Goes up.
It goes up. How many milliamps are flowing through this thing? This number right here is 100. It's about halfway there, so it's about 50 milliamps flowing inside of this. If I want to measure the voltage, I can use a voltmeter to do that. And what I need to do is I need to use the little dial and turn it to the voltage value that I would be trying to measure. So I have a bunch of little dials here. I have a 200 millivolts, 2000 millivolts, 20 volts, 200 volts, 500 volts. Which one of those voltages is closest to what I should be getting? 200 milli, 2000 milli, 20, 200, or 500? What should I be getting? How many volts are inside of it? How many volts? 3 volts. Which number is closest to 3? 200 milli? 2000 milli? 20? 200 or 500? I can write them down. Let's write them down. 200 millivolts. 2000 millivolts. 20 volts. 200 volts. 500 volts. 2000 millivolts. Voltage, put it to 2000, and I need to touch 2 sides of the light bulb to find out how much voltage is going on inside of this light bulb. When I touch both sides of this, what is it spitting out? Just a number 1. So if it does that, you just chose the wrong setting. What other setting might be good? 20. What do I get out? 2.86. Why? It's supposed to be 3. What the fuck? What happened? What did I do? My dumbass. I looked it up wrong. How many volts should I get? 3. How many am I getting? 2.86. How many volts am I missing? 0.14. What happened to those 0.14? This is more than 4 minutes ago. What was it? What was it? Resistance and current inside of the battery. So the ideal voltage that you have, the EMF inside of the batteries, isn't what you get out because some of it is eaten up inside of the resistance inside of the circuit. So that's why I'm getting 2.84. I'm not getting quite that total amount. And notice, I don't have to hook this up into the circuit to measure that voltage. An ammeter, I do have to hook up into the circuit. I could replace this ammeter with this guy. I could put this guy inside of the circuit and measure the current that I'm getting out that way too, if I want. So I can turn this all the way to 200, and then instead of having the ammeter in there, I can hook up this guy. Here. All I need to do is make sure that metal is touching metal, and I can electrocute myself. Metal is touching metal, and what am I getting out? 65 milliamps, which is about the same as what I was getting out. I just need to hook it into the actual circuit. Right? And if I try to hook these back, the light is on. And if I take these little probes and I put them on either side of this, I don't get an accurate value. The ammeter to get good measurements has to be inside of the circuit. Okay. This is all very practical stuff, all very useful. You can use it to wire your house. I don't recommend it because you probably blow out everything inside of your home. Okay. So that's practically how we do it. And then how we do it in a physics problem, we're going to do example 21.5 from your book. So I'm doing an example that you have worked very thoroughly inside of the book, so you can compare what we do to what the book shows you. So the book gives you a picture of a circuit. Circuit looks like this. We have a wire that comes up, and then we have these kind of jaggedy lines. What's up with these jaggedy lines? What are they? Those are resistors. So I have these little jaggedy resistor things. I'm going to have a little piece on that side. Little jaggedy resistor there. And we'll come down. Let's put a... What's the little short line next to the long line? I have jaggedy lines, which are resistors. What's the short line with the long line? Negative and positive of what? What does that represent? That whole thing.
The junction.
This is a battery.
Yeah.
Yeah. That's all.
Okay.
Short line with long line is battery. Jaggedy lines is a resistor. If I wanted to put a capacitor in here, what would I draw for a capacitor? What does a capacitor look like? Two little lines, right, two parallel to each other. Okay, so I could add a capacitor in here if I want. They told us values for all these things. They told us this this resistor over here is equal to 2.5 ohms. They told us that this battery is an 18-volt battery. They told us this resistor is little r1, which is equal to 0.5 ohms. They told us that this resistor is big R1, that's equal to 6.0 ohms. This resistor on the right-hand side, R3, is 1.5 ohms. And this resistor down here, R2, is 0.5 ohms. And then this battery down here is 4.5 volts, or 45 volts. Okay, so this is an example that is in the book. They've given you this picture, and then they drew some things into that picture. We're going to draw some things into the picture too, but we're not going to solve it the exact same way that your book does, and we're going to see if we got the right answer. Anybody feel like gambling? Should we gamble today? Okay, let's gamble. And what I will do is I will not look at the solutions that I just wrote up this morning while I solve this. And we'll see if we get the right answer. We'll see if we get the same answer as the book. If we get the same answer as the book, then this is fair game for your exam. If I make a mistake somewhere, then this kind of Kirchhoff's problem, I will not put it on your exam. Fair? Okay. This is very algebraically intensive, so get out your calculators. It's a lot of algebra, so I got to take off the blazer and roll the sleeves up. Make sure that I'm not cheating on anything, nothing hidden up my sleeves. And we're going to do a crap ton of algebra. So the Kirchhoff's law problem, there's two rules that we have to follow. What are the two rules in Kirchhoff's laws? There's a junction rule. What does that junction rule say? Current in equals current out. And what does the loop rule say? Sum of voltage in a closed loop is equal to 0. So the first thing I always do when I'm solving these problems is I find the junctions. So a junction is a place where you're going around the circuit and the current inside of that circuit can split. It can choose a path that it takes. So I'm just going to start somewhere. I'm going to start at the battery. I'm going to start up here at the negative part of the battery. And I'm going to go to the right through this little circuit that we have. So I go to the right, and I reach this point. Is this point a junction? Does my current have a choice of where it can go? No, it's got to go down. And then yell out stop when I reach a point where the current can move in a different direction, okay? So I'm going to start here. I'm going to go. Keep going.
Stop.
Stop. There's a junction. Because my current, where can my current go? Current can go left, current can go down. So that's going to be a junction, and I'm going to mark that junction. I'm going to mark it with the big red dot. Okay, at this point from this junction, where do you want to go? Do you want to go to the left or do you want to go down? I don't care, it's up to you.
Left.
Left. So I go to the left. I'm going to go through the junction. I'm going to go this way. Tell me to stop once I hit another junction. If I hit another junction, there might not be any more. Stop. That's it. Why is that a junction? I could go up or I could go down. Okay, so there's another junction.
What's the difference between big R and little
The size of the resistor. I think your book just uses if a resistor is less than 1, then it gives you a little r. If it's bigger than 1, it doesn't. Okay, what happens if we would have taken this junction, if we would have gone down? Tell me when I hit another junction, okay? I'm going to go down. What happens when I get to here? Where can I go? I can go left. Can I go anywhere else? No, so that's not a junction? Okay. Keep going. Is this a junction? No. How about this? Is this junction? No. How about this? Is this a junction? Oh, damn it. There's no more junctions. Oh, there's a junction, but we already marked it. Okay. So how many junctions do I have? 2 junctions. Okay, there's my 2 junctions. Now what we need to do is we need to decide what direction the current is going and how many currents we have inside of the circuit. So to decide how many currents we have, we need to look at the junctions, and at every single junction there's going to be some current going into that junction and some current leaving that junction. And every single line in this is going to have some certain amount of current inside of it. Yes? Yes, please.
What exactly are we figuring out this problem? What are we looking for?
Right, so in the example they tell us we're supposed to find what the currents are in every single piece of the circuit. Okay. And they gave us resistors and voltages, so we know all those. So whose law are we going to use to actually do this? What things? I know voltages, and I know resistors. What do I not know? I know V, I know R. I don't know I, so I need to find this current. So I'm going to use Ohm's law, a whole bunch of this. We'll see how. Okay, so I need to draw currents. And currents go through each different piece of this circuit, and I have some current going into a junction, and I have some current leaving that junction. So I think the easiest place to see some current is really this middle line. This middle line, it's just one line, one wire. So there's going to be current going through that. Do you want the current to go left, or do you want the current to go right? Doesn't matter, who cares? Pick. Right or left?
Right.
Right? Okay, so we're going to make the current go right. Current is going to go right through this. I'm going to draw current in blue. Here we have some current. That's the first one we drew. It's going through the first resistor, R1. So why don't we call that I1? Yeah. So I have some current leaving this junction, and that current's going to leave from this junction on the left, and it's going to go into the junction on the right. Now I need to identify where else there's current. I have this piece up here. I'm going to have some current leaving, so maybe I want some current going into this. So maybe I draw the current going in up here. So let's draw that current going in. What should we label that current? On this piece of wire. What do you think we should call that? This is I1 going through resistor 1. This is maybe I2 because it's going through R2. So we'll call that I2. Current only splits at junctions. Is this a junction? No. So what current is going through this top wire? Current only changes once you get to a junction. So that's got to be I2. Still the same current going through that top piece of wire, the top part of the wire. So this actually wraps around and gets to here. How about it here? Does the current change here? No, because that's not a junction. So this same current I2 that's going over here is going down, is going along that piece of the wire too. Right? But the important thing is the direction of the current doesn't change at the different places. So in this part of the wire, the current's going down. For the current to be going down in this part of the wire, I need to look at this upper part. Can the current go left, or can the current be going right and still have it going down on this part, if it's got to be completely consistent? The current has to be going to the left, so that when I get to this point, the current will be going down. So the current direction stays consistent. Okay. So I have a junction, I have some very important thing. I have current leaving and I have current entering a junction. You need to make sure that there's always some current entering and some current leaving your junction. So there's one junction. This junction, do I have current coming in? Yeah, I1 is coming in. Do I have current leaving? Yeah, what current is leaving? I2. Okay. So you make sure that you do that. And then do we have any more currents in the circuit? Any other wires that we haven't labeled? Yeah, we haven't labeled this bottom part. But this bottom part is just like the top part. So we have some current going through there. We can label it. Let's do current going through this whole loop. And what direction do you want the current to go? Do you want it to go down and left and up, or the opposite way? Do you want clockwise or counterclockwise? Doesn't matter. What do you want? Clockwise? Let's do clockwise. Okay. Clockwise current. Okay. So I don't know if the students, if the closest table to me can see. These are the solutions that I drew. The picture that we drew, do they match my solutions? What's different? I1. You picked I1 going the opposite direction to what I chose when I wrote up the solutions. So these solutions, can I just blindly look at these? Will these help me? No. Damn you.
Wait, do you not have to label the bottom one?
Do you not have to label what?
The bottom one?
No, we still got to put it. We still got to label. What should we call this one? I3. Sure. Okay. All right, let's have some fun, at least as much fun as you can have in a physics class, sadly. Let's draw the junction rules and the loop rules. So junction rule. Junction rule says current into a junction has to be equal to current out of a junction. I'm going to label my junctions. The left one I'll call junction 1. I'll call the right one junction 2. Junction 1. What currents are going into junction 1? I2. Anything else going into junction 1? I3. Anything else going into junction 1? No. What is leaving that junction? What arrows are pointing away? So I2 plus I3 equals I1. Current in equals current out. How about junction 2? What currents are going into junction 2? I1. What currents are leaving junction 2? I2 plus I3. So the junction rule just gave us, how many equations did we get out of the junction rule? Really only one, right? Because these are the same equations. I2 plus I3 equals I1, and I1 equals I2 plus I3. Okay, so technically we wrote two equations, but they say the same damn thing. So this is only one equation. How many unknowns do I have here? How many variables, things do I not know? I know all the voltages. I know all the resistances. I don't know I1, I2, or I3. So how many unknowns? 3 unknowns. If I have 3 unknowns, how many equations do I need to solve for all of those unknowns? 3 equations. How many equations do I have?
Oh, wait, 3. Wait, 1.
I only have 1. Damn it! How many more equations do I need?
2.
I need 2 more equations. So where can I get 2 more equations from?
The second rule.
Let's do the second rule. What's that one called?
0.
Let's see, loop rule. Voltage in a closed loop equals 0. Actually, I'm going to move the loop rule so that it's down here, because we need lots of space for the loop rule. The loop rule tells us the sum of voltages inside of a closed loop is equal to 0. So what that means is I imagine drawing a little loop-de-loop where I start at a point in my circuit and I go around that circuit and then I end at that place where I started. I like to draw loops that start at the batteries. So I'm going to start at the negative side of this battery and I'm going to go around and through the different parts of the circuit, and you're going to help me decide where to go as I reach places. Okay, so I'm going to start my loop right here. I'm going to call this loop number 1. I'm going to start right here at the negative part of the battery, and I'm going to go over through this part, and then I'm going to go down, and I'm going to read a junction. In this junction, do you want to go down, or do you want to go to the left? To the left? Let's go to the left, to the left. We go to the left. And to make this an actual loop, we want a closed loop. So to draw a closed loop, I need to end where I finished. So at this point, I get a junction. If I go down, I can't get back to where I started. So I can't draw a closed loop. So my loop, what direction do I have to choose the loop to continue going? I have to choose for it to go up. So I'm going to have that loop go up and reach that battery again. So we'll call that loop number 1. I can draw a second loop. Second loop, we have a choice. We could draw a second loop that's around the whole outside. I can draw a second loop that's just this bottom part. What do you want? Whole outside or bottom? Got the outside? Okay, again, that's completely different than the solutions that I just made, so who knows what's going to happen. It's crazy. Okay, let's go over. Let's go down. Go over. Go back up. And we're back to where we started. So there's my 2 loops. Thank God for multicolored pens. When I was an undergrad, the professors used, did any of you ever have to use overheads in classes? Like transparencies, and they'd shine things up. They always wrote in just one color, so this was all in like a black marker with really bad handwriting. At least now you get colorful markers in really bad handwriting. So let's do loop number 1, and what we need to do is we need to add up all the voltages that are inside of this loop. Voltages are batteries. So every battery has some voltage, but every resistor has voltage too, because there's current going through the resistors. How much voltage, how do I calculate the voltage through a resistor? Multiply the resistor times the current that's going through that resistor, and I get the voltage. So every single piece of that circuit has some current inside of it, and I need to add up all of those. So I start right here on the negative side of the battery. I'm jumping from the negative part to the positive part. So I'm going from a smaller side to a bigger side. So that means I'm adding voltage there, because I'm going from negative to positive. So I'm going to add 18 volts. I'm going to add plus E1, positive E1. And then I'm going to the right to this top part. That's the direction I chose for my loop. So my loop is going to the right through resistor R1. Can you see that? Does that make sense? Yes. What direction is my current going through R1? I drew the current going the opposite direction. So if your current is going the opposite direction to your loop, then you actually add the voltage change in that resistor. So I need to add because the directions are opposite. So I do plus. What's the current that's going through that? What's I through this little resistor? What is that I? I2 is in that upper part, yes.
I have a question.
Yeah.
So if you are using the, so say, would you be able to just turn into the other direction and then you subtract it?
Okay.
So that's what
Yeah. As long as you're consistent with following the rules, doesn't matter what directions you choose, everything will work out. So we'll go with what we drew for now. So that's what current's going through that resistor? I2. They're going opposite directions. So it's positive. So we have plus I2 times what? We have to do current times resistance. What's the resistor? Little r1. I2 times little r1. And then I get to this point in my loop. At this point, I go down. Any resistors over here? No resistors over on this part. So I get to this point. At this point, where am I going according to my loop? I'm going to the left. So I'm going to go to the left. I reach my resistor big R1. What direction am I going through R1 according to the loop? I'm going to the left. What direction is my current going?
Right.
To the right. So they're going opposite directions. So do I add or subtract this? I add this. What's the current going through that? What's the current in the middle section? It's I1, so that's plus I1 times big R1. And then I reach my other junction. I get to my other junction. I'm going up through this junction. What direction is my current going inside of this resistor? Going down. The opposite directions, so do I add or subtract? I add. What's the current going through that resistor? That's plus I2. And what's the resistance? Big R2. And then I keep going up. And where did I get to? I got back to where I started. So that is my closed loop. I add up, these are all voltages. I'm adding up all voltages here. What is that equal to? 0. Voltage in a closed loop is 0. So now I can plug in some numbers. What is E1? E1 is 18 plus I2 times R1. Do I know what I2 is? Nope, that's what I got to solve for. Do I know what little r1 is? Yep, what's little r1? 0.5. Plus I1, don't know the currents, times big R1, which is 6. Plus I2 times big R2, which is 2.5. That's equal to 0. So what I'm doing now is just algebra. I'm going to add up everything, multiply everything together. So I'm just combining like terms. So I plugged in my numbers and then added like terms. 18.5 times I2, 6 times I1, 2.5 times I2, and then I combined the I2s, 0.5 I2 plus 2.5 I2. So you get 3.0 I2, 6 times I1, and 18. And this is all equal to 0. Okay? That's my first loop. Any questions on the first loop? Good with the first loop? Let's do the second loop. This is going to get tricky. It's going to get tiny. So second loop. We started up here at 18 at this E1. I'm going from the negative side to the positive side, so that's going to be plus E1. I'm going to go around my loop. I'm going to the right through resistor R1. My current is going to the left, so that's going to be adding that. So I'm going to have plus I2 times little r1. I get to the corner. I go down through the corner. I keep going down. I'm going down in this bottom part. That's my loop direction. What direction is my current going through in this resistor? My loop's going down, the current's going down. So what do I do there?
Negative.
I have to subtract this, so I have to make this negative. So that's going to be plus a negative I3 times big R3. Because the loop and the current are going the same direction. So then I get down to this corner. My loop is going to the left. What direction is my current going?
Left.
My current is going to the left, so because they're going the same direction, I have to subtract off that voltage through that resistor. So that's going to be plus a negative. I3 times little r2. Then I get to my battery. I hit my battery, and I'm hitting the positive side of the battery and jumping from a positive number to a negative number. How do I go from a big number to a little number? Can I add?
Subtract.
I have to subtract. So I'm going to subtract off that voltage. That's going to be plus a negative E2. And I'm going to keep going. I get to the corner. I'm going up. I reach this junction. I'm going up. My loop is going up through resistor R2. What direction is the current going?
Down.
Current is going down, so I add the I2 R2. What does that equal to?
0.
That equals 0. So now we got to plug in all these numbers. Holy moly. 18 plus I2 times R1. I2, R1 is 0.5. How many points is this worth on an exam? Say your exam is 100 points. How many points should this be worth?
50.
150? Maybe. This is a long, involved problem. I3 times little r2. Negative 45 plus I2 times big R2 is 2.5. With these problems, the challenge is finding the loops and then doing the algebra. I recommend writing out all the steps of the algebra. Use lots of paper for this. If you try to do things in your head, typically you get caught. Make dumb little mistakes. So 18 times 0.5 I2 plus a negative 1.5 times I3 plus a negative 0.5 times I3 plus a negative 45 plus 0.5 2.5 times I2. Zero. Let's combine like terms. What's 18 minus? Combine the numbers. 18 minus 45. What do we get there? Negative 27. Okay, let's combine all the things that have I2. I have 0.5 I2, and then I have 2.5 I2. What's that? 0.5 I2 plus 2.5 I2 is 3.0 I2. And then I have a negative 1.5 I3 plus negative 0.5 I3. What does that get? minus 2.0 I3 equals 0. Okay. So now we have how many unknowns? Still 3. How many equations do we have now? We have this one, and we have this one, and we have this one. So in these problems, it's always the same process. You identify the junctions and write an equation for a junction, and then you identify 2 loops and identify those 2 loops. If I gave you some circuit that had 4 currents that were unknown, how many equations would you need? 4. If I gave you 5 equations. If I gave you 10 unknown currents, just give up. Give up at that point. Don't even try it. Okay, so let's rewrite these 3 equations that we know and do a bunch of algebra. So we know I1 is equal to I2 plus I3. We also know that 18 plus 6 times I1 plus 3 times I2 is equal to 0. And we also know negative 27 plus 3 times I2 plus negative 2 times I3 is equal to 0. I'll let you catch up on writing all of that down. While you write down all of that, we're going to write I1. We need to get 4.75 amps, positive or negative. I2, we need to get positive or negative 3.5 amps. And I3, we need to get negative 8.25 amps. Made any mistakes, then this won't work, and you won't get tested on it. Okay. Oof. This is stressful. I could still make mistakes now. So what we want to do now is you take your junction, and inside of your junction, anywhere you see one letter, you can replace it with the other 2 letters. So I know I1 is equal to I2 and I3, so I can get rid of I1 by plugging in I2 plus I3 everywhere that I see an I1. So in this equation, I have 18 plus 6I1 plus 3I2 equals 0. Everywhere I see I1, I can plug in I2 plus I3. And then I get rid of that I1. So let's do that. This is a systematic process. Will work for every single one of these problems that you do, no matter what. So I have 18 plus 6 times I2 plus I3 plus 3 times I2 is equal to 0. So I have now used first equation and the second equation. And what I'm going to do, I'm going to simplify the second equation. I'm going to simplify that to be 18 plus 6 times I2 plus 6 times I3 plus 3 times I2 equals 0. Keep doing some algebra. Let's see, that's 18 plus, looks like 9I2 plus 6 times I3 equals 0. What I want to do now is I want to solve for one of these variables, either I2 or I3. I don't care which one. Pick one. Which one do you want to solve for? You want to get I2 by itself? Okay, so we got to get I2 by itself. So we want to get everything else on the other side and figure out what I2 is. So let's subtract, what would we do? We'd subtract 18 and subtract 6I3 from both sides first, probably. So I would have then 9 times I2 equals negative 18 minus 6I3. My I2 still isn't all alone. How do I get I2 all alone? Get rid of that 9 by dividing by 9. Divide both sides by 9. And I now have I2 is equal to, let's see, what's negative 18 divided by 9? That's negative 2. Minus, what's 6 divided by 9? It's negative 2/3, which is, let's do it in decimals. We'll get a slightly different answer than what we should get. That's okay. 2 divided by 3. Or 6 divided by 9. Uh-oh. It's a bad number to get at Catholic school. It's 0.666. 0.667. I3. Okay, so that's what I2 is. Great. I2 is equal to all of this. Now I can go back to this third equation that we have. The one that we haven't used yet. I have negative 27 plus 3 times I2 plus a negative 2 times I3 equals 0. What do I do with this? Plug in I2 everywhere I see an I2. So now I have negative 27 plus 3 times negative 2 minus 0.667 I3 plus negative 2 I3 equals 0. So that's negative 27 plus 3 times negative 2 is negative 6 plus 3 times 0.667 that gets me 2 plus negative 2 I3 equals 0. Right, so negative 27, 3 times negative 2 gives me negative 6. 3 times negative 0.667 gives me negative 2 times I3 plus negative 2 I3 equals 0. Combine like terms, so we get, what's negative 27 plus negative 6? I don't trust my math. 27 plus 6, what is that? Negative 33 plus negative 4 times I3 equals 0. Need to keep solving. So I have negative 4 I3 equals negative 30. Move the 33 over to the other side, so I get positive 33. Divide both sides by negative 4. Oh boy. Make or break moment, I3. $33 divided by 4. What do we get? What do we need to get? Well, what do I want to get? I want to get 8.25. What do you want to get? Anything else, because that means you're not going to get tested on this. But what do I get? Negative 8.25. And that's current, so what are the units on that? Amps. Okay. That's one down. All right. I could test you on it still. Yes. Check. How do I find I1 and I2? I can go back to my prior equations, right? So I know I2 is equal to this. So it's equal to negative 2 minus 0.667 times I3. And I3 is negative 8.25. Okay, let's see. Negative 2 minus 0.667 times negative 8.25. What did everybody get? Pop that into your calculators. What do you got? I got 3.5 amps. What were we supposed to get? 3.5? Okay, 2 down. 2 down. Only 1 more to go. 1 more to go and I can put this on the test. This is exciting. You're all very excited, I can tell. Okay, so I2 we found was 3.5. I3 we found was negative 8.25. Take nothing for granted. Negative 8.25 plus 3.5. I got negative 4.75. Got it. Can I put this on the exam? Oh, sorry. Yes, I can. What do the negatives mean? Can you have a negative current? All the negatives mean is that you chose the wrong direction for the current. The current actually flows the opposite direction. So we got a negative current for I1, right? So because we got a negative number, we said that the current is going to the right. The current is actually going to the left. That's not a problem. That negative would correct that and show anybody that came along to analyze your circuit that the current actually goes the opposite to what you chose. Okay? It's fine to get negative numbers. That is how you do Kirchhoff's laws. This wasn't one of the problems. This is example 25.1. So you can see how they solved it in the book as well. So you have multiple problems that you've seen solved with Kirchhoff's laws. Okay?